All right, we're going to have to tuck in the sort of summary of the pair deck discussion here on this video because we're just not going to have time in class. But I wanted to share some things with you. So in this first slide here, you can see the variety of paths that people expected the ball to take after it leaves the point B in the hoop here where the break was. Some folks kind of expecting it to curl like that. Some people expecting it to veer away. Some expecting it to go in a straight line. And of course, if you watch the video, is this going to work? What's going on here? Yo? Why can we not watch the video? There we go.
Take it.
Clearly it's moving in a rather straight line there. So let's watch that one more time.
Take it.
Okay. So then it falls on us to try to explain why is it moving in a straight line like that after it leaves the hoop. The direction of that straight line, by the way, it's tangent to the circle. And so that was something that we didn't discuss earlier, but that led into this idea of V-tan, okay? Because the path it's going to take is tangent to the circle. You can even see somebody drew over here a radius and then demonstrated that this was 90 degrees. So why is it doing that? And also, why is it not doing that before? So if we look at the free body diagrams that folks were drawing here, these were a couple of examples people threw out there for A. So we've got gravity down, smoosh poosh, ball, comma, floor up. And then here this person has drawn smoosh poosh, ball, comma, hoop, pointing that way, which is towards the center of the circle, okay? This friend over here has 4 arrows. And so the question then is, well, what is the source of this force? What interaction is that? Because the ball's touching the floor, we know there's smoosh poosh there. The ball's touching the hoop, we know there's smoosh poosh there. The ball's near the earth, so gravity for sure. I demonstrated with the other video that friction is more or less negligible. That ball's more or less rolling around at a constant speed, so it's not friction. And so we have to reject that force, and we end up with a free body diagram like this. And then you add these arrows, okay, and you see that there's an unbalanced force. And if you think about the direction of that unbalanced force, it's always changing because it's always pointing perpendicularly away from the hoop. But that would have it always pointing towards the center. And so for that reason, I'm going to give this unbalanced force an extra label here. I'm going to call it a FOOC, an unbalanced force towards the center, okay? And we can kind of relate this all together because, again, if we think about B after it leaves the hoop, what's the free body diagram going to look like? You're going to have gravity down. You're going to have smoosh poosh up because the ball's touching the floor, but it's not touching anything else. So this is your free body diagram. That's a free body diagram for an object that's got a constant velocity. It's traveling in a straight line at a constant speed. The only difference between after B and what's happening at A is that at A, it's touching the hoop. That's one interaction, a smoosh poosh interaction because of touching. And when we take away that one interaction, we're left with this. And this kind of explains to us why is this thing traveling at a constant speed in a straight line, okay? When we talked to our friends about the different models that applied, for A, there were some differences in the free body diagrams drawn, but far and away, most people identified that as being UBFPM. And then B, after it's left the hoop, not quite as decisive a victory, but here we have 37 for balanced force particle model, okay? That's based on the interactions that are occurring. And there were some really great insights offered as to the question about, well, is it accelerating while it's in the hoop, okay? And I really appreciate the science of some of these folks here. They're explaining that it kind of goes against what their intuition is, but the diagrams surely seem to indicate that, yeah, it must be accelerating. So over here, magnitude of the velocity doesn't change, but technically its direction changes as it moves around the circle. I'm not entirely sure if that counts as acceleration because the magnitude remains constant. The first free body diagram would suggest it is accelerating as the forces are not balanced. And so that's it exactly. So if you think about this thing as it goes around in the circle, if we look at its velocity at this position, that velocity would be tangent to the circle. Okay, so that means it's going to be perpendicular to the radius. If I look at it at some other point over here, it's going to be tangent to the circle at that point. These arrows have the same length, but they're pointing in different directions. So when I get up to this point in the circle, and I draw my tangential velocity, again, it's always 90 degrees with respect to the radius. So if you consider this to be V1 and this to be V2, we want to talk about the change in velocity. That would be V2 minus V1, okay? If we want to do that in terms of arrows, it's sometimes helpful to recognize this as V2 plus the opposite of V1, okay? So if you look at these two arrows, if I go to add them together, first I'll draw V2. Oh, come on, man. First I'll draw V2, and then I'm going to draw the opposite of V1, okay? And maybe I should just do that right over here. I'm going to draw the opposite of V1. It's going to go like that. Okay, and those things have the same length. That's the opposite of V1. And if you look at the combination of those, results in an arrow that's going to kind of point off towards the center here. And this would be the change in velocity. So you can see the direction of the change in velocity here, and I'm being a little bit loose with my geometry, but the direction of the change in velocity here, if I make that interval small enough, more or less pointing towards the center. So that's further evidence to support what we're seeing here is an acceleration that points towards the center. That's called a centripetal acceleration. Okay, centripetal. That means center seeking, for those of you that speak Latin. Center seeking acceleration. Okay, that acceleration is neither pointing in the direction of the motion nor opposite the direction of the motion. It's pointing towards the center. So if this velocity is perpendicular to the radius, this acceleration is pointing along the radius. If I was going to draw a vector for the acceleration, I mean an arrow, sorry, then that would be always pointing towards the center. That's the A sub C, the centripetal acceleration. Okay. And again, what's causing that centripetal, or what's associated with, cause is kind of a dangerous term here. But why is there a center-directed acceleration? That's because there's a center-directed unbalanced force. Okay. Is it really accelerating? What direction is that acceleration? So here were some of the responses to the question about where the cork would be in the bottle. And you can see that some friends have that cork pointing towards the center. Some friends have it pointing away from the center. Some friends have it kind of pointing in the direction of motion. Some friends have it opposite the direction of motion. Some friends have it dead center in the bottle, which would indicate no acceleration. Okay. And then I don't know if I brought the video over for this one. Did I do that? We can just pop over here and check it out real quick.
All right, there's the cork at rest, floating straight up in there.
It's not
And when
accelerating.
I give this a spin,
Ooh. Now it is. Okay, and so if I pause it there, you can kind of ever so slightly see that it's inclined towards the center.
you can kind of see which direction that thing is pointing.
Okay, ooh, can I back it up a smidge? Arrow buttons? Nope. Yeah, there you go. So you can see it's pointing in towards the center. And if we look at it from above here in a second, come on. There we go. Let me pause it so that you can see it. It's kind of tough to see the cork in here, but you can see how this air bubble is piled in towards the center. And just like the cork,
Maybe notice that the
That-
air bubble kind of acts
that air bubble floats in the water just like the cork does. So I assure you the cork is right underneath this thing, pointing towards the center of rotation.
like an accelerometer as well. So if you can't see,
Yeah, you can kind of see the cork right there. Okay, so that clearly kind of solves what's happening there with the cork. It's pointing towards the center. There's acceleration towards the center. That's the centripetal acceleration. Okay, so we needed to do all that so we could establish the lab that we're going to do here. And this lab is going to look at a relationship between the force and the motion, okay, on a really general level. So if you look at the apparatus again, I can just click that from over here, apparatus. And I'm trying to, yeah, okay. So if I pause this right here, you can clearly see the stopper is beneath the mouth of the tube. So the string is kind of pulling at an upward angle here, all right? And the big thing that I needed people to identify, the forces on this hanging mass are balanced. That means that the gravity pulling downward is balanced out by the tension pulling upward. The tension pulling upward here, well, the stopper's connected to the same string. So this tension pulling at this angle matches the tension pulling up on the hanging mass. So, that allows us to sort of make a logic chain here that if I know this gravitational force, because I know I have 100 grams of hanging mass, so that's a Newton, means this tension here has to be a Newton. Well, that means that the tension on the stopper is a Newton as well, okay? And I massed the stopper. The stopper itself is only 10 grams. So that's only going to be a tenth of a Newton. So those forces aren't anywhere close to the same length. When you look at everybody's drawings, you kind of have a default arrow length. But a lot of people had correctly identified that this force, and this force are all the same value. Okay, it was just kind of how they're angled and how the relative values of those forces compare. If you look at this diagram, if I scale the tension, it's really not up angled by much. Okay, it's not horizontal, but it's not that far from it. So in the end, I scaled this so that the tension was 1 meter here. That would be a Newton, and this was a tenth of a meter here to be the tenth of a Newton. When I measure this part of the triangle, this is my unbalanced force here. It's perfectly horizontal, which means it's pointing towards the center, so I should really be calling it a Fuch. It roughly equals a tension. This is like an isosceles right triangle where the hypotenuse and one of the sides are pretty darn close to the same length. So my argument then is that if I know the gravitational force, I know the tension on the hanging mass. If I know the tension on the hanging mass, I know the tension on the stopper. Therefore, I know the Fuch being experienced by the stopper. And then ultimately what we're going to do in lab is try to get at one of two questions. What's the relationship, if any, between Fuch and omega? Or what is the relationship between Fuch and Vtan? Okay. Omega is the angular velocity in radians per second. That's just 2 pi over big T generically. And then Vtan is the distance around the circle in meters, 2 pi r, divided by the time around the circle in seconds, the period. They're pretty close to each other, right? This one's times r, this one's not. So if I wanted omega from Vtan, I would just get rid of that r. If I wanted Vtan from omega, I would have to multiply by r. Okay, that's how those things relate. Anyways, if your stopper number is odd, you're going to plot Fuch on the vertical axis versus omega on the horizontal axis. And if your stopper number is even, you're gonna plot Fuch on the vertical axis versus Vtan on the horizontal. Okay. The rest of this is just the pre-lab stuff that we're going to discuss in class, but you need in Desmos to just input your measurements directly. And a note, you're going to need to include the stopper number, 1, 2, 3, 4, 5, the stopper mass, okay, and the stopper radius. And I have an image on Canvas that shows you how to measure the stopper radius. Hopefully you did that right. And then you should have your data table. Your time for 20 laps goes in X, and your grams of hanging mass goes in Y. And then later you're gonna see on Canvas how to make Desmos then plot Fuch versus either angular or tangential velocity. So that's about it. Hopefully this kind of helped firm up the understandings from the Pear Deck a little bit for you.